Uh, Sorry, everyone. Not really sure what happened. I just like suddenly the whole thing just stopped and
Okay, so
I
you were
had to
hearing
restart.
me okay. It wasn't that you stopped it because you stopped hearing me.
No, no, no. It was just somehow like I was just listening to you and suddenly everything was going away. I don't know
Right.
like if I
Okay.
I don't think I accidentally like pressed something, but who knows?
For me, it said that you ended the call and I had to
Yeah, no. I
reconnect.
also got a message that the organizer ended the call, but it wasn't like I didn't press any button. So
I'm blaming
anyway.
I'm blaming I'm blaming Alan for that.
Right, guys.
Well, let me get back to the. I'll share the screen again, and then I guess people now have to watch two videos if they want to know the whole story. Okay.
Okay. Um, yeah, so I think I got to the emulation piece. So ideally you would target your entire SoC design in its sort of soft and chipletized form into an emulation platform. Oh, and I was saying I took a little bit of a digression of I'm seeing a sort of a number of these SoCs have like got a bit of eFPGA, embedded FPGA in them, where they know their hardened interfaces like the IO types, memory and transceivers, etc. And maybe they even have pieces of IP like maybe a RISC-V core or some sort of encryption engine or dedicated hardware acceleration piece. But they want to integrate some fabric into that, some FPGA fabric into that to keep some of their options open, maybe in the device. So, but point three is saying, well, you would do an entire 100% FPGA emulation platform. And obviously these platforms do exist from a historic perspective, but I'm wondering if we could actually make a very elegant SoC, chipletized SoC emulation platform where you have the chipletization or the interfaces is part, built into the emulation platform design, that you could stitch these things together in their chiplet form in the emulation platform. So you would get an emulation of the device, and ideally, if this was this would be some sort of modular emulation platform where emulation could also be swapped in and out with real hardware. So I'm saying if we assume that we have this chiplet emulation platform has some sort of bridge chiplet, should we say, that was available so that real chiplets could actually be readily attached to the rest of the emulation that's going on. You could have something that I historically termed, in my world, we built simulation engines to test defense systems, missile systems. And what we did is we put simulations in the loop with the real weapon system hardware, and we called it hardware in the loop. So forgive the acronym, and the way the acronym is spelled, HWIL, is a little bit funny compared to the term hardware in the loop, but you'd put real hardware in the simulation loop, and that was how we tested the weapon systems. So I was thinking we could have a hardware in the loop, as in when a real chiplet arrives, we could put a chiplet, attach it to the emulation engine. So as you get real chiplets, you can actually start to build. You can start to build your test environment.
Sorry, Alan, sorry to interrupt. Can you please explain again what is hardware in the loop means? Because I heard this, but I just missed your explanation.
Yeah. So effectively, the idea is if you've got an emulation platform. So the perspective from what I'm trying to say here is assuming you've got an emulation of your SoC, 100% emulation, but then one of the chiplets of your emulation actually really does exist, and so you say, well, okay, I would like to bring the real chiplet into the equation, but still emulate everything else. And so if there was a bridge chiplet, like that could bridge into the chiplet interface, at the chiplet level, like the half a picojoule per bit bunch of wires interface level, then you could actually plug a real chiplet that then gets attached into the emulation environment. And we call that like hardware in the loop. It's you've got an emulation platform, but you're putting real hardware, real chiplets into the loop of the emulation environment. That would be That would be the idea. Does that make sense?
Yeah, and is there any other counterpart like software in the loop?
Oh, well, yeah. So in terms of simulation, obviously, I said you start with a software simulation, and potentially you can, you know, in an emulation platform, there is a layer. There will probably be a layer of software that runs on the SOCs in the emulation. So you certainly have all of that as well. So you have the whole application is the idea. You start off with all of the application, including all the hardware simulated in software, and you can run the job. It might take, you know, a year to run a 1 second job in pure software. I don't know. But basically, or these higher level simulations are you know, they're not clock cycle accurate. They're more higher level models, software models, right? So yeah, you introduce the emulation to emulate the real hardware, but your software still is in the software world, obviously. So yeah, the interfacing here is at several levels. But what I'm saying is we start out by thinking about this type of approach first. Is how are we going to bring, I'm designing a new chiplet, how am I going to bring this into the world? How am I going to, you know, so you think about it from a top-down perspective.
Yeah, but Alan, you need an FPGA chiplet, right? Because you can't just plug it into a Xilinx, because Xilinx, at least today,
and
right?
that, yeah, that's exactly right, Cash. So basically, that's where I said you would need. So on number 4, I'm saying you'd be assuming that a chiplet to emulation bridge chiplet was available. So somebody actually could take the IOs of an FPGA, be them the transceivers or the select IOs, and actually you know, convert it to a bunch of wires so that you could attach these real chiplets. So you wouldn't need a bridge chiplet, which is what I said in number 4. Make sense?
Yeah, no, totally. It's just, I think it needs to be more. Well, anyway, okay. Let's keep moving.
And so as more chiplets required for the SoC become available, you can continue replacing the emulation parts with real chiplets until your final module, you know, if you think of this in a modular type enablement form, until your final module is completed, the SoC, and it will all be chiplets. It will be fundamentally you've implemented your chipletized device. But this is all happening in a common modular system level modular architecture. So the module created both during simulation, emulation, hardware in the loop, and final SoC would be architected to be deployable in a real compute infrastructure environment. So you could actually start to use this. You could use it at the different stages, but when you're done, you're ready to go with the final chiplet implementation. And so you're learning an awful lot as you go. Hence, you have useful application that can be ran on the new SoC all the way from software simulation to final chiplet assembly. And then 7, I've just mentioned that the chipletized solutions could also present an initial lower cost, a way of taking a low volume product to market, a bit like FPGAs have always been sold of, don't cut your own ASIC, buy this expensive FPGA because it's far cheaper if your volumes are going to be less than 1,000 units a year, or whatever the number is. So don't spend the $30 million cutting your own ASIC when you can take a product to market with FPGA. But then your volumes get to a certain level, and then you say, well, below this, I can cut my own ASIC for the amount I'm paying for the FPGAs. So in a similar fashion, I can see that working for the chiplet world. It's like, well, I think a monolithic solution would be a good idea for my product. And actually, chipletized solutions may be damn challenging because of the assembly and the test and the known good die and the rest of it. But maybe those costs are not too bad in a lower volume environment, especially if I think when I get to the volumes I'm hoping I'm going to get to with my market opportunity, I can cut my own monolithic device at the right volume level. So it's a bit like the same FPGA mentality to ASIC from chipletized to monolithic. So I'm saying there, what have I said? I said chipletized solutions could also present an initial lower cost way of taking a low volume product to market before finally cutting a monolithic solution as volumes ramp and economies of scale tilt more towards a cheaper monolithic solution. And so that's the sort of the tenet of the idea. And then full disclosure, I've been sort of advertising my OCP high performance compute module that we've been developing as a very interesting potential modular architecture that we could execute this approach on. And we are in the OCP HPC sub-project, we are actually looking to build an emulation platform first out of our wall of compute with these modules. So we're putting the emulation piece in place. You could do the software simulation and emulation with our architecture to begin with. So that's what we're doing in the OCP HPC, independent of ODSA. But I would like to think we can join the two worlds together with this type of approach. So that's what I'm trying to do.
Sounds very interesting. I think one thing I'm trying to understand a bit better is, like, I get the idea of kind of moving from a high level software simulation and then going further down. Once you get to that level of having part simulation and maybe one or two chiplets, how do you envision this physically happening? Would you then like take that chiplet, add a bridge chiplet that goes from, say, a bunch of wires to Ethernet or something else, and then plug that into this big compute wall that does all the emulation of the things that haven't actually been built in hardware?
That's the idea. Yeah. So let's say to your point, let's say you've got a chiplet that interfaces to Ethernet. But this module, which I'm talking about, the HPCM module, is architected with a bunch of I/O on it for different purposes. It's very generic purposes, actually. So it can be allocated to different bus standards. Protocol agnostic is at the modular level. But basically, this module would be pluggable into a real world. Like it could be pluggable into the good old-fashioned entire computing stack. But as you bring chiplets, so first of all, the emulation platform will be connected into the real world through its transceiver and various interfaces. But as you introduce the chiplets with the chiplet bridge, that can then replace the emulation platform connecting into the real world. So you always have an end-to-end workable system. This is what the hardware in the loop means. It means that you have a full software to hardware stack running this device, albeit at different speeds. And obviously there's some challenges of when everything's not running at full speed, you have to slow things down in CANU and all that. So I haven't got all the answers here. This is thrown together I'm trying to deal with the top to middle part, whereas I think ODSA has been currently working from the bottom to middle part.
Okay, I see. So yeah, I think that was I think you didn't fully answer my question, but like basically, if I had a chiplet with a short reach interface, that like my assumption is a chiplet can only talk like, say, tens of millimeters at the most to the next thing. So how do you connect that to the emulation?
Well, obviously the a chiplet would only talk tens of millimeters to the emulation FPGA via this.
Oh, I see. Okay.
Bridge.
Gotcha.
Via the emulation bridge bunch of wires interface or whatever. So to interface the FPGA I/O to the real chiplet. But assuming that it's an I/O chiplet, if the I/O chiplet has an Ethernet interface on it, that can talk 30 dB, right? So yeah, or whatever it can talk. So suddenly you actually I've hot off the press, you can be the first guys to see the module that I'm envisioning, and at least you can. I don't know if this will help anybody, but at least you'll get a bit of an idea about what we're thinking of here in terms of the modular piece. Is that?
You want to share a screen for?
Yeah, I can do a quick share of screen. This is the first animation that we've got out the door, and we're hoping to build a 3D model of this as well that I can bring to OCP. I was hoping that maybe I could get one of those benches.
They seem in high demand.
Yeah, I saw that. So, are you seeing a picture of a module?
Yep, we can see
Okay, so this is the HPCM module fully assembled, but I just run this animation so you can see. So first of all, you can see some I/O on this. This is roughly the size of an OEM module, if you know the OCP accelerator module, but there is no motherboard. Everything's connectorized and module connections. But essentially, if I run the video, you can see you've got the traditional big CPU at the bottom. A little zoom in, and all of these connectors at the top. So that's your your H100 or your FPGA. Well, we'll be putting a big emulation FPGA on the first one of this, and then that's a water cooled thing for the chip at the top that could be a kilowatt. We've got conduction cooling for these CXL.MEMS or SSDs or other I/O. You can put cabled I/O in this module as well. It doesn't have to be media, but you can have your media attached, and then you have these topology I/Os, which these ones are currently CXL PCI Express, but you could have some Ethernet ones in there instead for your topology interface. And so just running it again, in my chipletized world, I'm saying this substrate, if you look at the size of the substrates from the likes of AMD now, they're like getting 80 millimeters by 80 millimeters. So it doesn't, we could make this a substrate, the organic substrate for chiplets, and get rid of the middleman, get rid of the package. And I've talked to IBM, Fraunhofer, and a few others about the potential of going for that. So this would be where we could implement the organic chiplets on here. Obviously, silicon, you could also put, from a CoWoS perspective, you could put a CoWoS assembled device into this module and get rid of the CoWoS package that they normally have around, with the solder bumps. Just put the CoWoS straight down onto this substrate as well. So these are the areas that we're looking. So I'm looking at chiplet enablement with this platform. I'm also trying to tackle CXL enablement with all the things that are going on the CXL front and all the challenges of getting CXL run out. If you follow the composable memory systems work group in OCP, you'll see we've got a lot of work to do there. And then this module, by the way, then there's a wall of compute. So this animation at the moment doesn't show it very well, but if I can pause, it won't let me pause. If you see there. So basically, these are the power pins bringing 48 volts in. These two are water inlets and outlets. So effectively, this module blind mates onto a wall. So you have what I call a wall of compute, and then you can have tens of thousands of modules to make up like a frontier supercomputer. And so that's the idea, that you would modularly put these, so you could make a very big emulation platform by connecting these modules together, or you could integrate a real chiplet into the emulation platform by putting a chiplet down on this module with an FPGA, with a bridge to an FPGA for the emulation piece, or you continue to rebuild this module until all of the chiplets are in this module format, and then it plugs straight into the rest of the system, and you can run applications. And if your SoC interfaces to a CPU or a GPU or an AI chip, depending on how it exists, obviously this doesn't necessarily make sense from an embedded IoT type chiplet solution, but it would at least get you to a working little simulation world. And then you could go away and build your miniature device with your chiplets for the IoT application. So again, it's a sort of so it's a consistent platform from simulation to emulation to chiplet in the hardware in the loop to your finalized chiplet design.
Gotcha. Okay.
Yeah, I think this is great, Alan. I think it will really solve a problem for a lot of people. And as you know, we're working on FPGA chiplets, right? And then also options for chip scale packaging. And it's exactly for this type of application where a customer wants to emulate or even go to production. In our case, we wanted them to also go to production, right? So anyway, I think that this is a great direction.
The other nice thing about this, guys, I don't know how many of you were actually at the DOE OCP workshop, but from the work groups, there was two separate work groups that said the government could help by sort of building this prototyping type platform where funding, that sort of thing, to get this up and running, this sort of ecosystem up and running. What can they were asking, what can they do to start to pull this together? And I think the missing piece is the big guys. They're vertically oriented, they do everything themselves, and we've got a bunch of small guys all coming together with their pieces, but but there's nobody there to stitch this together, and that's where we need the help. And this doing it around an architecture like this could be interesting. By the way, I also attended the ERI, the Electronics Resurgence Initiative summit a couple of weeks ago, and I discussed what I was doing here in the photonics breakout work group, and the photonics people are desperate for a similar type of a platform where, in fact, Ayar Labs and Intel have got extremely excited about this, because they're saying, we actually looked at the OEM module for putting the Ayar Labs and Intel chips down on, and Song, who runs that group, the OAI work group in OCP, is saying, the OEM module as it stands isn't very sympathetic to optical fibers coming out of the top of it, whereas this is entirely designed, and that is where I need to talk to Ayar about this. The idea is that all of the I/O comes out the back, and therefore you're not, it's not a mess. It's a lot neater. We are a cable first solution, for good reason, electrically, signal integrity wise, and migration to optical, be it near packaged optics or co-packaged optics. And so, like I say, as a systems engineer, I'm trying to cover everybody's bases. Chiplets are just one small, deep vertical that I'm trying to work with, but I'm trying to work with the thermal guys. This has got immersion cooling in a very small area, is what we're trying to do on one side, conduction cooling on the other. It's I'm bringing all of these disciplines together and breaking down the silos, and I tell you, it's tough, because everybody sees a little piece of what I'm doing in their world, and they think, well, okay, I can see the benefits, but it's not really that big for me. It only looks big when you look at it across the different disciplines. And the key driving force of what we're doing in OCP HPC is sustainable, energy centric. This is energy centric first architecting for domain specific computing. So it's doing what the likes of Google, Tesla Dojo, Google TPU v4, NVIDIA DGX or Grace Hopper, or even the likes of Cerebrus. You've got all these proprietary things going on at the system level. We're trying to do this in an open world and make a new IBM PC for the world of computing as we have today. Anyway, on that note, I'll shut up. So, Marek, I don't know if that's enough, or you want me to try and put more in there, or does that get the idea started? Marek, you're on mute.
We lost Marek now.
I think he's on mute.
Oh, sorry. Yeah, sorry.
Okay.
I'm back. No, I think this is good. Initially, when we were talking, I think I had in my mind that the last one or two bullets that you had about like using this as an alternate way to prototype and using chiplets kind of as an intermediate step. I now see that kind of this plays into like that there's a whole methodology around building a system. So I'm currently thinking, like you just put it down here in the introduction, and I'm trying to think of where this could go best
absolutely.
in the document.
I didn't know where to put it.
No, exactly. That's fine. So I'll figure this out.
I just thought I'll throw it in the introduction as I gave it the name approach.
Yes.
So
yeah.
The approach that I think we might want to consider taking. How are we going to approach this?
Yeah, I think like lengthwise, I think this is pretty good, even though I know there is obviously more information needed for people to fully get the idea. What I was also going to talk to other people about is if you have links or like kind of additional documentation and or even a talk or slides that people could follow up on if they want to know more about this, I think that would be helpful to keep the use this as kind of an intro for people to learn about the idea, and if they want to know more, then they can follow up based on additional literature.
Yeah, actually on that, I've got loads of sort of presentations in piecemeal. I did give the ODSA. There is a recording in the ODSA that I gave.
Right. Yeah. So then we could have put a link to that, for example, in there. Yeah.
Yeah, that would be a good one. But I'm also doing a 15-minute update for everybody at the OCP Summit. And I'm trying to, because I've come from so many different angles, I'm trying to give that top-down view to give everybody the big picture as to what we're trying to achieve. And I have a slide on chiplet enablement in there, as well as CXL enablement. So I think that will give people a really good high-level perspective without diving too deeply into the chiplet piece. The chiplet piece, I think, was covered quite well on the ODSA recording because there was a ton of great questions from Cash and others that got into some of the weeds that I thought was really quite good. So I think my OCP Summit presentation with the ODSA one would be good.
Okay, sounds good.
Obviously, the Summit presentation won't be available till October.
Yeah. Kash, I want to make sure that we have time to cover your additions to the document. I can share my screen again, so that people can see where we're at. I'd seen there was a bit of an addition here under next steps, and I'm not sure if but there's also the open marketplace where you added things. So let's
do the next steps one, because I think that's something I added earlier today. Yeah,
and I think they partially have the same. So you have this image here and this one, and I think those are, at least this one is also in the market. Like they're both.
Yeah,
in the
no,
so
I just edited from something else and
consolidate. But let's just talk about.
Exactly, you can consolidate as needed. I just put it in a separate section because I was applying it for, why it's important to do interop, right? Because I think the industry, this is actually a big issue. I mean, because ODSA has been futzing around trying to put two die together, which at the end of the day isn't terribly useful. It's something, right? But this interop thing is a huge issue, and also security and how do people really do this? So I think this is what this section is addressing. And UCIe, I think, has taken a lead in this area. So
how much text there is.
So I've stolen their slide. Okay. And I think I assume it's from their white paper, so it's public. I don't think it's anything that we shouldn't we should have concerns about, but I'll let Bapi worry about because they'll sue him, right? So that's always good. We'll put Bapi's name here. But the idea that you need to have golden die, how do you test, and what are the actual test problems that you can solve, right? So I think they've actually taken a really good step at that, because so if you go down the curve onto their drawing, and I recommend people to actually look at their white paper. I think we should link to their white paper, right? They've actually proposed essentially a golden die kind of idea, where at least somebody can bring on that golden die and check interop, and then they can even put it on the same module, and then they can have that golden die be driven by an external FPGA, right? So that's the kind of what they have proposed. And what we have done is now in the next section, I just added that I think last week, Quick Logic, and we introduced the fact that we are developing an FPGA chiplet. And now there's two uses for that. And basically, we haven't gone out and really exposed everything we're doing, but we're basically going to have the UCIe on all four sides. We're also going to have two of our IoT PHYs. Essentially, these are a bunch of wires, 8-bit slices that we're proposing to ODSA, right? So that's whether it becomes a standard or not, I don't know, but we'll have 2 of those, so we have the same amount of bandwidth on the bunch of wires as well as UCIe. Okay.
So then why
and
is this called X4 then? Like you're saying 8 bits, is
yeah,
it?
this is an older slide.
I see.
We're now thinking that when we actually did the math, the by 8 actually is only like 10-15% bigger. Okay. So so on the host, so there's a host and an endpoint in terms of our IoT proposal, right? So so on the host, which is what this FPGA would be, the host actually supplies the clock to the IoT device, and those 8 bits can actually be switched on as all RX or TX or a mix of 4 and 4. Okay, so it's the equivalent. It's more complicated than just saying. So I'm talking now verbally. If we haven't released all this, we're talking with BAPI and team technically on whether it can be accepted. But this is the basic idea. So in theory, you would have 8 bits, so you would have a total of 16 bits, which you can split as RX and TX. So you could do 12 like TX and 4 RX for asymmetric type applications as well, right? And but for the IoT side, now on the IoT device, you could actually hook up a 4-lane device to this 8-lane device. So that's why it still has this by 4 kind of idea. Okay.
Gotcha.
So that's kind of and the idea here is frankly, validating that they connect electrically is actually not really the big issue, right? I mean, simulation tools are really, really good. I think there isn't really going to be much gained by, I mean, I think there is something to be gained by validating it, but it's if today people can't make a 16 gig serial link work, then you know electrically you've got an issue, a real issue. The link layer is a completely different thing, right? Because everybody's interpretation is going to be different. It's software driven or state machine driven. The implementations are going to be different. The standards are going to be changing. So connecting a third party UCIe device or a bunch of wire device, and then having an FPGA where you can also change the link layer, right, and debug it, I think will be very critical. So that's kind of our view. And then we are going to make these FPGAs also chiplets be available and chip scale package, so customers don't have to spend $1 million and do a custom substrate. And so that's why I'm very excited about Alan's OEM module type approach, where you could put 10 or 20 chiplets on a module, and some of it could include FPGA, some of it also could include PCIe or Ethernet or some of the other protocols like optical that some people are wanting to play with. So I think having so our view completely aligns with this wish to be able to emulate a system, except we're looking at it more from a commercial standpoint of not just emulating the system, but also then if somebody says, hey, I want to go to production with this, we can enable that for low volume, right? They can just buy these chiplets without having to go through a whole substrate design and testing and dealing with known good die. They would have it in a known good package, right? So that's kind of what we're doing. So
Cash, can I clarify, when you say is this just the UCIe PHY itself, or do you have the full UCIe stack inside the hardened inside, or is that soft in the FPGA?
We haven't announced exactly what we're doing. Okay. But there is going to be a hardened stack as well as a programmable stack, obviously, so you can debug things.
Okay, and so but bunch of wires, if bunch of wires shared the same PHY, you wouldn't be able to switch between bunch of wires and UCIe, for example.
We have that's the reason why we have bunch of wires. We don't specifically say here that the by 4, which is really a by 8, will be bunch of wires compatible, but it will be bunch of wires compatible. So okay. You'll be able to bridge from.
Oh, so you'll have both bunch of wires and UCIe, but they'll be separate. Yeah. They will be different IO. It's not you could make the same IO one or the other.
Exactly. Well, that's what we're showing on this
Right,
on this
right.
drawing,
And
right?
last question.
And so you will be able to bridge from the 8-bit to UCIe. That's the basic
Right,
hope
right, right,
to be
right,
able to do with the FPGA. Sorry.
Right. Okay. Well, actually, a couple of other things. So you mentioned 16 gig on UCIe. Now the UCIe spec goes down as low as 4 gig.
Right.
And when I talk to others, some of the IoT type applications, UCIe is just so overkill. But 4 gigs sort of gets you down to, I mean, that's for a bidirectional link, you're at 16 gigabytes per second. I think it works out at if you go at 4 gig. Aggregate transmit receive, which is still pretty high. But is that, do you think that's usable?
We're working with Vapi and the technical team on a proposal for an IoT 8-bit solution, right? So on the IoT device itself, you can go down to 4 lanes if you want, which will hook up to this 8-lane thing, right? On the host, it's 8-lane, so it's more, it has more flexibility. But in the IoT device, you only need 4 lanes.
Right.
And those 4 lanes could be 2 RX and 2 TX.
Oh, nice. Okay.
You can split each one can be on RX or TX, or if you want all 4 TX, like for an ADC type application, you could do that, right? It's programmable.
Right. Okay, that's good.
So it's roughly like a quarter to 1/8 of the area of so for an IoT device, it's actually smaller than if you just did GPIO.
Right. Okay.
So it actually economically makes sense.
Right.
And the other thing is that you can provide the clock from the host device. So this FPGA could provide the clock to the IoT device. So the IoT device doesn't necessarily need a dedicated PLL, which is a cost that a lot of people are worried about.
Okay, and you're showing this as purely and entirely chiplet IO FPGA. Are you planning on having any big transceivers, 30 dB transceivers, or?
Yeah, there are other chiplets that are in process for PCIe and Ethernet and.
So in reality, then we could use one of your FPGAs as the bridge chiplet between a big emulation Xilinx FPGA and.
Correct.
And a bunch of wires are UCIe. So there you go. I'm your first customer.
No, I get it. And then later on, they can put other chiplets of ours or whoever's and integrate, right? So yeah.
I like it. Yeah. Well, there you go. If you've got general IO and we can stitch one of your small devices to a big Xilinx emulation chip, then we've got that bridge we need.
But it would also it would actually bridge to an IoT type device too with using our device, right? So that's basically the idea.
Yeah. I like it.
There's one more thing I want to bring up while everyone is here, which is what I had briefly mentioned before, this thought of trying to weave in some of the literature that people are familiar with, like either be it good talks like on YouTube or wherever, or white paper, like other white papers or something. And I've been starting to put together some of those and put them in here for people to follow up on specific topics. So I had in the introduction, which I've been working on, but we can talk more about this next time, I've been writing down a couple of white papers that I'm aware of from like the last year or year and a half that describe chiplets in general, which I would want to reference in the beginning of the document so that we don't basically have to cover everything in absolute detail, and rather focus this white paper on the things that are new ideas or that are not sufficiently covered. And I think this whole idea would also be applicable for, say, test and probe, or for chiplet packaging. I can talk to Trent separately, or even for the standardization. I know we have this the reference to the proposed, or like to this document from the ODSA about the proposed chiplet standard, so we can link that. But anything else, I think that would be great if people could, even for now at the end of the section, just put a couple of references, and then we can either weave them into the text or leave them as references afterwards, which would help so that we don't have to cover everything. is that something like, say, Rajesh or Kash and James and so on, that you'd be able, like do you have links like that in mind that we could add?
Yeah, I think that's a great idea. I mean, I certainly will try and come up with some, and I think I think once we've got the white paper sorted and what we want to put in, then I think it you know, where it flows, like, you know, you have to act, it's the editor, right? And then
Yeah.
I would put all those at the end, and also events that are happening. So if somebody's interested, here's some events that are happening, you know, like the Chiplet Summit or OCP Summit or whatever, right? For the next year or something, whatever we know of, right? So the more information somebody has right there, I think the more useful it will be. That's just my my view. Yeah.
Okay.
Yeah, I agree. That's a good idea.
And what has been said and cast as well. Especially, I think maybe this will be good also put as references. Not only this, right? I think also another section of the white paper. I think probably we should also starting adding some. I think so there many like UCIe and other references. So it's good to add in that. I think I start numbering them, and they'll be good there. I think there's some standardization like white paper that we have from the CDS. Definitely we can reference here, which I plan to reference as part of my section as well.
Okay, excellent. And Boon, I had seen your addition here about the interfaces and the addition of Open HBI, which is here. You had suggested like making the table bigger by one column. I wanted to see, like, my understanding is that Open HBI is not being like worked on anymore. So I'm wondering if it, like basically what interfaces we, even as the most common ones that we should be looking at. Like, I guess the same thing is true for AIB, but there are, like, let's say, real products out there, and to my knowledge, more existing chiplets. So what do people think? Should we like also put Open HBI in here, or focus on things that like seem to have a future, say?
Well, that one I would
think
definitely go no on the HBI.
Okay.
Yeah, HBI, Open HBI is dead, right? So I mean,
it exists as a standard boon, but there's literally no support. I mean, even the work group has disbanded.
Yeah.
Right.
Yeah.
Okay.
I didn't aware of this earlier, so it's okay to remove it.
Okay, sounds good. Then yeah, no problem. Like that's why I'm bringing it up, just to get other people's input as well. Okay, excellent. Then thanks everyone for the additions that you've made. My goal for next week is to go through this document and mark up things a little bit more. I've started kind of looking at the links of sections, but haven't had a chance yet to read through all of it. But I hope next time we can start discussing, or like I can present a couple of suggestions on how we can make this a little bit more cohesive.
Sounds good.
All right.
Thank you.
Awesome. Thanks,
Thank you,
everyone.
Thank you, Marek. Bye.
Bye.
Cheers. Bye.
Bye bye.
Thank you.